All right, later today I'm going to put up some old exams that I've given in the past, exam ones. So you can start looking at that. I'm planning on writing your exam one tomorrow. And like I said at the beginning of the semester, I will be telling everybody what types of problems to expect in general terms on the exam. And there actually are going to be two forms of the exams that are slightly different. You won't know which form you'll get. The problems will be basically the same, different numbers, maybe different orders, maybe slightly different things. You will get one of those two versions. I do ask that people that are in the in-class class take the exam here at this time. Actually, we'll start at 9 o'clock for the exams at 9:05. And if you're sick or something like that, or you have some other reason you can't make it, then we can try to figure out another time. But otherwise, as a default, make sure you come here on Friday for the exam. The online people are going to be taking it at various possible times, either next Thursday or next Friday. Next Thursday, the time slot for you, and by the way, you'll have an hour and 45 minutes for the test. Though I hope to make it so that you can finish, say, in an hour and 15 or an hour and a half. So there'll be an hour and 45 minute time slots on Thursday for the online people, starting at 8, 10, noon, and 2 is the plan. And then on Friday, there will also be an hour and 45 minute time slots for you. One of which could be the same time as this group, 9 o'clock, but if everybody's here for the in-class class, they will be pretty much filling up this room. So you'll have to take it at some other room, the testing center probably at 9 o'clock on Friday if you want to take it on Friday. Or another option could be at near my office at I think 2 o'clock in Wood as well on Friday of next week. Did you have a question?
Yep. So it goes to like 10:45 then, or?
Yeah, 9 o'clock till 10:45.
Chapel.
Yeah. If you have a real big need, like if you were part of a worship team or something, then we could try to pick another time. But yeah, so that's going to go through chapel time next Friday. Any other questions at all?
Is it next Friday?
Yeah, Friday of next week, yeah. It'll cover all of chapter 1 and at least the first section, maybe also the second section of chapter 2, plus some Mathematica things and these extra reading assignments. Again, we have to decide what's a reasonable thing to know for those extra reading assignments since they are extra technical and difficult. I do want you to learn some things, and again, today I'm shooting for the last 10 minutes of class to talk more about that. All right, 3 main things I want to do today. First of all, I want to go through a lot of phase line / bifurcation examples. Actually, I'm going to go to make it efficient. I took the code from your completion key for the completion homework to do today, and I'm going to go through those same examples to really try to solidify the ideas in your minds. Second thing is we want to start section 1.8, which is about linear equations, special kind of equation that have a new kind of symbolic technique that's different from separation of variables. And finally, the last 10 minutes we'll shoot for the stuff about the extra reading assignments. All right, so let's take a look at these examples. I'd like to go through these examples pretty quickly, but try to highlight the main things to know. Where are they here? They're down in this section here. Titling this Bifurcations and Bifurcation Diagrams for Families of Autonomous Differential Equations. In the general form, dy/dt equals f sub alpha of y, though sometimes the alpha is an a instead. I actually prefer using alpha because, I don't know, using Greek letters kind of emphasizes in my mind that it's a parameter. But sometimes we'll use the letter a. Okay, these are families of differential equations. This is not just representing one differential equation. In fact, it's representing infinitely many differential equations. We're going to think about infinitely many differential equations at the same time. That's the first thing to realize here. The a in this first example is the parameter. Whenever you think about one of these differential equations, you imagine thinking about one particular value of A. How do you think about infinitely many differential equations at the same time? Essentially, we're thinking about all their phase lines at the same time. And wondering how the phase lines change as A changes. That's the big picture. When you have a big change occurring in the phase line, like two equilibrium points merging and annihilating each other, so to speak, that is a bifurcation. Some big change in the phase line. I'm not talking about changes in individual solutions as A changes. I'm talking about an overall change in the phase line. So for this example, dy dt equals f sub A of y equals y squared plus A. We want to think about how the phase line changes as A changes. The first thing to do is think about what are the equilibrium points and how do they depend on A. You find equilibrium points by taking the right-hand side function and finding its roots. Set this equal to 0 and solve for y. That'll give you the roots of the right-hand side function as numbers, which are going to correspond to equilibrium solutions of the differential equation as constant functions with graphs that are horizontal lines, which then go back and correspond to equilibrium points on the phase line at the locations of the equilibrium solutions. So we set this equal to 0 to find those equilibrium points ultimately. That equation is equivalent to y squared equals negative A. Take the square root of both sides, plus or minus, to allow for both square roots, and you get that equation, which only is going to give you real numbers when negative A is non-negative. Giving up two real, okay, let's write it. Let's go ahead and write it that way. Two real equilibrium points when negative A is positive, so that the thing under the square root is positive, and you get a plus or minus that are just two distinct real numbers, which is equivalent to A itself being negative. One real equilibrium point when the plus or minus doesn't affect it, when you have square root of 0, which is 0. A equals 0, and no real equilibrium points, 0 real equilibrium points. When the thing under the square root is negative, negative A is negative, which is equivalent to A itself being positive. Okay, so A equals 0 is the value of the parameter where this big change occurs in the phase line, going from 2 equilibrium to 1 at one value of A to no equilibrium points. That's the bifurcation value, or bifurcation point. Sometimes I may call it a value. Sometimes I might call it a point. It's probably better to call it a value, but sometimes people use the word point. What would the phase line look like in each of these cases? Question.
Can you kind of explain like what the bifurcation, like why A equals 0 is the bifurcation value?
That's what I'm getting to do.
Oh, okay. Sorry.
One thing I said was that it's because it's where the big change occurs in the number of equilibrium points.
Okay.
Okay. You might wonder, though, I mean, the word bifurcation is kind of strange. I'll talk about where that word comes from here in a second.
Okay, thanks.
What you want to make is a bifurcation diagram here. Ultimately, what's a bifurcation diagram? Essentially, it's a picture of a bunch of phase lines. A bunch of vertical phase lines. This is going to be a y-axis here. Different phase lines for different values of A. The horizontal axis is labeled with the parameter. It's okay, we can do that. what does the phase line look like in the three main cases here? A is negative. A little bit better. I want that to be vertical. A is negative, A is 0, and A is positive. How can you, what's the quickest way to figure out what the phase line looks like other than just knowing how many equilibrium points there are? I'm also talking about the arrows. What's the quickest way to figure it out in your head? I hope you've tried to develop skill at this based on the completion assignment. It's related to this function. What should I do with that function? You want to get this. This is really important. And we have talked about it. You look like you want to say it.
Me?
Yeah.
Set it equal to 0?
That helps you find the equilibrium points. And that's important for this function. And it's, think visual. Start with the G. Graph it, yeah. We've graphed it before. Graph it, that's the key. How? Well, it's a quadratic. Its graph is a parabola. Make the y-axis horizontal here. How can you graph it when you don't know A? Well, you could pick things for A. A is the vertical translation here. When A is positive, the graph looks like this. That's when A is positive. When A is 0, these are supposed to be vertical translations of each other. The graph looks like that. And when A is negative, the graph looks like this. They're all vertical translations of each other. That is not a solution curve. None of those are solution curves. I've said that before. Very, very important. You realize this is not graphs of solutions. This is not the slope field. This is a picture of the graph of the right-hand side function, and the important point is, where is it 0, where is it positive, where is it negative? For what values of y is it 0, positive, and negative? That's the key. That helps you figure out what the slope field looks like, because it helps you find equilibrium solutions, and it helps you figure out where solutions are increasing and decreasing, and it helps you draw the phase line. This is super important, okay? This is probably the most important thing to get out of chapter 1, is this kind of thought process. Anyway, when A is less than 0, or in this case, we've got two roots at plus or minus square root of negative A. This would be negative square root of negative A. This would be positive square root of negative A. Whatever A is, I could pick A to be negative, excuse me, mistake, sorry. I could pick A to be negative 1, or negative 2, or negative 3, whatever. It's the same general picture. So you've got these two equilibrium points equally spaced from 0 here at square root of negative A and negative square root of negative A. How do you tell which one's a sink and which one's a source? Or could they be nodes? How do you tell? You can tell with the graph. You want to say?
When it's positive, then you know that there is going to be up, and when it's negative, there's going to be down.
When it's positive, when y is less than negative A, yeah, the arrow is going to go up because the outputs of the right-hand side function are positive, meaning your derivative for your solution curves are positive. Solution curves are increasing. Arrow goes up. Between these two values of y, the output of the right-hand side function is negative, meaning the derivatives of solutions are negative, meaning they're going down, they're decreasing, so the arrow goes down. Over here to the right of square root of negative A, which is a positive number, don't let that confuse you. Over here, the output of the function is positive, so the slopes of solutions are positive, they're increasing, the arrow's got to go up. So this thing here is a sink, this is a source. There's something called a linearization theorem, which I haven't talked about in class. It's in the book, section 1.6, that says when you've got an equilibrium point and the derivative of the right-hand side function at that equilibrium point, in this case, is negative. The slope of this curve right here is negative. When that occurs, that's going to mean that equilibrium point on the phase line is a sink. Makes sense. The right-hand side function is going to change from a positive value to a negative value in that situation. I am assuming this thing is an equilibrium point, so it's a root of the right-hand side function. That's going to make it go from positive to negative, which means values below the equilibrium point correspond to solution curves that are increasing, arrows that go up, and values right above it correspond to solution curves that are decreasing, so the arrows go down. A equals 0 case is this one. There's only one equilibrium point at the origin. Y equals 0, focus on that y-axis there. Otherwise, the output of the right-hand side function is positive, so solution curves are always positive otherwise. So they're always going up. And this is going to be a node. And then finally, when A is positive, this graph is always above the horizontal y-axis. The outputs of the right-hand side function are always positive, meaning slopes of solution curves are always positive. So solution curves are increasing. You get a phase line like that. Yeah, visually the bifurcation value occurs at the value of A, where this change from two equilibrium points to 1 to 0 occurs. Why is it called a bifurcation? Where does that word come from? Well, if you graph both of those things as functions of A here, what you get is a sideways parabola showing a curve of equilibrium points, so to speak. Careful how you interpret that. It's not literally, this is not a, it's a picture of a bunch of phase lines, remember? I could, in theory, draw infinitely many phase lines, infinitely many vertical lines. Anytime I draw one of them, where that intersects that curve, those correspond to equilibrium points on that phase line. This one being still a sink, this one still being a source. Linearization for this one says that since f sub a prime of square root of negative a is positive, the slope there is positive, that's going to mean that this equilibrium point is a source. Which again makes sense because we're going from, the fact that that slope is positive means you're going to go from a negative value to a positive value as you pass through that equilibrium point value. It's not easy stuff, okay? But I'm telling you the main things you need to know, how you need to think about these. I've got the Mathematica code in here. This draws the generic bifurcation diagram here. I've got a bunch of phase lines in there. How many phase lines did I draw? 1, 2, 3, 4, 5, 6, 7, 8, 9. These vertical lines, 9 of them, are all phase lines for different values of A. The blue curve is, I guess I didn't say where the word bifurcation comes from. Well, bi means 2, okay? Furcate, I don't know the root of that. Bifurcate kind of corresponds to the fact that if you let A go decrease here, you're kind of going from no equilibrium to 2. Emphasis on the 2. Actually, bifurcations don't have to result in 2 equilibrium points. They can result in 3 or 4 or 5. But oftentimes they're 2, and so that name is stuck.
What does it have at the origin? Why does it have the arrow pointing down?
That's a mistake. I don't know why that's in there. Yeah, I didn't make it perfectly. That should not be there. Thanks for pointing that out. I made an animation of the same thing too. Well, actually, this is not really the bifurcation diagram. It's showing you the relationships between all these things. I'm letting A change, and we're seeing how the phase line changes. That corresponds to the slope field changing on the right, and corresponds to the right-hand side function, its graph changing as A changes on the lower left. it would make that label very big there. But you get the idea? We're seeing the phase lines change as A changes. We're considering infinitely many differential equations all at once. We're focused on the qualitative features, the nature of the phase line, rather than the detailed quantitative features like formulas. We're not worried about formulas. Oh, that takes a long time. Well, probably better just consider one more example here. How about this one? I mean, you can consider these other ones again as you study for the test next Friday. So there's the family. This time I did call the parameter alpha because that's what the book called it. dy dt equals f sub alpha of a, f sub alpha of y equals y to the fourth plus alpha times y squared. How would you think about it by hand? Again, the first key is to determine the equilibrium points in terms of alpha. You find the equilibrium points by setting the right-hand side function equal to 0 and finding its roots then. Set that equal to 0. Hopefully it's factorable. In this case, it is. Y equals 0 is always going to be a root. You're always going to have an equilibrium point here at y equals 0. And y equals plus or minus square root of negative alpha. Kind of like plus or minus square root of negative a. Zero is always going to be there. You're always going to have at least one real equilibrium point. Evidently, alpha equals 0 is again the bifurcation value, because that's going to be where the change occurs. When negative a is positive, meaning negative alpha is positive, meaning alpha itself is negative, these will be two real roots here, and you're going to ultimately have 3 equilibrium points. When alpha is 0, you just have the 1 at 0. When alpha is positive, you only have 1 equilibrium point at 0. These become imaginary numbers, and we don't include them in the picture. The bifurcation value is again alpha equals 0.
An equilibrium point has a multiplicity of 2. Is that automatically a node?
Yep. Good realization there. Yeah, there's the graph of the right-hand side function. Let's look over here on the screen. When alpha is negative, linearization implies that this point ends up being a sink. The slope of this function is negative there. It's going from positive values to negative values. That's the really important thing. So take the equilibrium point there on the phase line. Underneath, solutions will be going up. Above it, solutions will be going down. It'll be a sink. This one ends up being a source. Yes, this one ends up being a node, and that's also called a double root. Why? Because of the y squared term over here, it's like y minus 0 quantity squared. That means 0 is a double root of this, and that means ultimately that it ends up being a node for this picture here. This one was a sink. This one was a source, which now, yeah, if you do look at it, that one's a node. The arrows are going down on either side of it. Oops, I drew that wrong, sorry. When alpha is 0 or above, you just have 1 equilibrium point at 0, and it ends up being a source. Why? Because watch this graph. As alpha increases, it becomes always positive. We're always non-negative. Is there a way you could know that by hand? Well, I guess the fact that the roots go away. You only have the one root when alpha is positive.
Is that a source then, or a positive node?
Oh yeah, I drew it wrong. I still drew it wrong, didn't I? Oh man, that was bad. I was not being careful. Yeah, it's not a source, it's a node. Thanks. If you were going to draw all the equilibrium curves, so to speak, one of them would be just this horizontal axis where y is always 0, and the other would be a parabola. Again, obtained by graphing essentially these two functions of alpha. Get the sideways parabola. Thanks for pointing that out. Okay, it takes work. It takes some getting used to. It's a really new kind of thinking for most people. But again, I'm telling you the exact way you want to think about these things. Okay, you can make plenty of really hard examples, by the way, for this stuff, where factoring, for example, is not possible. So we want to keep our examples possible to do. I will remark that oftentimes for the first exam, I typically give problems like this, just to make something up. All right, let's just call it alpha. And the key to figuring out where the bifurcation value occurs is to use the quadratic formula. I won't sing it this time. Set that equal to 0 and solve for y. In terms of alpha, those are the equilibria, and you're going to have two of them, two distinct real ones. When 25 minus 4 alpha is positive, you only have one real equilibrium point when 25 minus 4 alpha is 0, and you have no real equilibrium points when 25 minus 4 alpha is negative. So the bifurcation occurs when 25 minus 4 alpha is 0, or alpha is 25 fourths, 6.25. That would be the bifurcation value. When 25 minus 4 alpha is positive, which is equivalent to alpha being less than 25 over 4, then you'd have two equilibrium points, two real. When this is negative, which means alpha is greater than 25 fourths, then you don't have any. We seem to be always encountering cases here where the bifurcation occurs like this, so to speak, as alpha changes. But they can occur the other way, like that. By the way, maybe it would be better to call this a trifurcation, in a sense. I don't know. It's like, that's more like a pitchfork on its side there. Trident. All right, on to the next subject. Linear first-order differential equations are differential equations of this form, in general. And I'm about to show you a method for solving such equations. Today, at least in the case where a of t is a constant. This method has an official name, fancy sounding name, method of undetermined coefficients, but we can also just call it educated guessing. Okay, that's the method really. Educated guessing. So let's consider a particular example. I'll show you the method. I'm not sure if I'll have time to fully explain why it works. I will allude to why it works. Actually, the proofs in this section are definitely ones you want to study, because they are the types of proofs that sometimes I have people do on tests. Okay? I'm probably not going to do proofs today, but maybe on Friday we'll do a proof or two related to this. So here's an example. dy dt equals negative 2y plus, oh, let's make it e to the 5t right there. That equation is in the right form. The coefficient of the y is the a of t. In this case, that's a constant function. A of t is always -2. And the thing you add over there, that's the b of t. The linearity of this equation comes from the fact that it's linear in y, not t. Okay, the key thing about linearity is you can't have any squares or cubes or square roots in y. It's got to be a first power of y with some either constant coefficient, or it could be a function here. A of t could be some non-constant function. It would still be a linear equation. The nonlinearity in the b of t, that's irrelevant as far as describing this as a linear equation. We will see why for sure on Friday. It's also called non-homogeneous since b of t is not the zero function. If b of t were the zero function, I don't mean the number zero, I mean the zero function. It's not the zero function. If it were zero, it would be called the homogeneous equation. Okay, it turns out. And to do our educated guessing, what we first do is we consider something called the associated homogeneous equation, where b of t is zero. This is a different equation, okay? This is not the same equation as that one, but it's obviously somewhat similar. It's related. It's associated. This is a non-homogeneous equation. This is the associated homogeneous equation, which is simpler, and in fact is so simple you can guess the answer. You don't even have to separate variables. What's the general solution of this? General, I'm not talking about any initial value problems here. Let's use a C. Solve it by guessing.
The opposite of y squared? Oh, no.
No?
e to the negative 2t.
E to the negative 2t. I'm glad you guessed anyway. It's okay. We're after a function whose derivative is -2 times itself. This is an autonomous equation. Any constant times e to the negative 2t has the property that its derivative is -2 times itself for all t. It's conventional to not just call this y here, but y sub h. The h corresponding to homogeneous. This is not the general solution of the original, but it's going to be a piece of the general solution, we'll see. What else do you do in this method? We're not done. This is step 1. Step 2 is to guess a solution of the original non-homogeneous equation. I mean, we guessed this, and it was simple enough that we definitely could guess fine. But how in the world are we going to guess a particular solution of the original non-homogeneous equation? Which I'm going to rewrite like this. I'm going to add 2y to both sides and write it like this. Why did I write it like that? Because it actually helps you guess better. That's the reason. It's also another standard form to write the differential equation. How could you guess an answer here? Well, we're after some function whose derivative plus 2 times the function always equals e to the 5t. That's what this says. I probably shouldn't guess something involving cosine, or sine, or tangent. How in the world am I going to get an e to the 5t out? I probably shouldn't guess t squared, because there will be no e's that will come out from differentiating that function plus 2 times itself. I probably better guess something involving e. And I probably better guess, in fact, e to the 5t. But that wouldn't work, would it? Could we be so lucky? The derivative of e to the 5t is 5e to the 5t. Plus, that would be another 2e to the 5t. That would be 7e to the 5. Yeah, that doesn't work. But it's closer, at least. The way you guess in this kind of example is you do guess something involving e to the 5t, but you allow yourself an undetermined coefficient. That's why it's called the method of undetermined coefficients in front of the e to the 5t. I'll call it capital A. We call it y sub p, p for particular. This is a standard thing to do. We're crossing our fingers a bit here, hoping that this will work. It does seem like an educated guess. This seems like a reasonable guess for a function. Maybe for a certain value of a equals 1 doesn't work, we already saw. But maybe some other value of a where the derivative of this function plus 2 times the function always equals e to the 5t for all t. We're going to have to find the derivative of this. There it is. We'll now substitute these things into the left-hand side of the differential equation. The left-hand side upon substitution becomes 5a e to the 5t plus 10a e to the 5t, right? No, excuse me, no, that's a mistake, sorry. 2. I was thinking 2 times 5. The derivative is 5a e to the 5t, I substituted that in right there, plus 2 times the function, 2 times that. That's where the 2a comes from. This simplifies to 7a e to the 5t, and I want, put an equal sign in the word want this to equal e to the 5t for all t. So, use a equals 1/7, that works. Seven a must equal 1, so a must be 1/7. Equate the coefficients. 7a with 1. You can double check that it works by plugging it into the differential equation. It'll work. Step 3, the general solution then becomes y equals yh plus yp. You end up adding them. C e to the negative 2t plus 1/7 e to the 5t. Take the yh, c e to the negative 2t, and add the yp. I didn't actually write that down anywhere except right there. 1/7 e to the 5t. That works. Let's see if Mathematica produces the same thing. I just type it in as a differential equation with no initial condition. I do need a y of t in there, even though when you write it by hand, it's just a y. Don't forget to use a capital E or a special E for the number e. Yep, same thing. That's the special E there. The C1 is like the C2. Add an arbitrary initial condition into here. Make it an initial value problem, though I won't pick a specific initial condition. I'll put an arbitrary one in here like I usually do. You know, on your homework you typically get specific initial conditions. But I like to try to emphasize you can do an arbitrary fixed initial condition. Though oftentimes it leaves it in unexpanded form, so do a post-fix expand here. That would be a way you can write the unique solution to an initial value problem where again y0 is a fixed but unspecified number. This represents infinitely many functions. This represents one function. Okay? All right, the last 10 minutes, what I think I want to do in focusing on those extra reading assignments is I want to focus on the second one. And the thing I'm really after here in the last 10 minutes today is to focus on explaining all these different notations that you see and different terminology in the context of, let's start with a simple example. Here's a simple example. We can take the same example we just had, actually, the associated homogeneous equation. I'll do the homogeneous one, not the non-homogeneous one. What do we write? We write the general solution of this as y equals c e to the negative 2t. I will not bother putting a yh because this is a different example. The unique solution to an IVP with y of 0 equaling y sub 0, I'll write it as a subscript by hand, is y equals, now I'm going to go ahead and use the phi notation even though the book doesn't, phi sub y0 of t equals y0 e to the negative 2t. The constant ends up equaling the initial value of y. That doesn't always happen. That is a solution. For a fixed value of y0, it's one solution. It's the unique solution of the initial value problem. I can plot this with manipulate in the slope field and see how the graph changes as y0 changes. You get it looking like that when y0 is positive, looking like that when y0 is 0, right? Y equals 0 is an equilibrium solution. And looking like that when y0 is negative. And y0 would be the y-intercept. This is in a slope field that I'm not drawing. Labeling your axes is very important in this class, right? You got to know what the axes represent. In the reading then, I say, okay, now I'm going to do something weird. I'm going to consider this to be something I call a full solution. This defines something called the full solution. That's my terminology, by the way. I think I heard one or two people in the past, my math professors call it a full solution. I saw in a book that I read, another person called it a complete solution. Full and complete are kind of synonyms. Still use a phi, but this phi is going to have two inputs, t and y. And this function is a function of two variables, t and y, that's essentially this thing on the right-hand side, except use a y instead of a y0. Emphasize that I'm going to think of y, the initial condition, the initial value of y as a variable. So it's the exact same expression, but now I'm thinking about t and y as being two variables for this function of two variables. I can think about this without thinking about the differential equation. In the differential equation, y depends on t. Y is the dependent variable, t is the independent variable. For this function, I could think about graphing that function without worrying about the fact that for the differential equation, y depends on t, if I wanted to. I could make a three-dimensional plot of this. Now, that's not a useful thing to do for the most part, but I could do it. What's more useful is to use yet another bit of notation. By the way, the reason I call this the full solution is it contains information, so to speak, about solutions of all possible initial value problems for that differential equation here. Which, of course, this contained that information as well. But I'm just thinking about this function differently. This thing is kind of an intermediate to what I'm ultimately after, something I often call the flow, though you really only should call it a flow when the equation's autonomous. This equation is autonomous. Now this is where it gets a little extra funny. I use a different Greek letter that looks like that for the name of this function. Actually, that's a phi too. This is kind of a plain phi, that's a fancy phi. How do you take it on Mathematica? Plain phi can be created by doing escape, ph, escape. Fancy phi, I don't know why, can be created by doing escape, j, escape. I don't know why j was picked. They didn't have any other use for j. Escape, j, escape makes a fancy phi. If you've ever used LaTeX, or ever will use LaTeX, LaTeX calls it var phi. V-A-R-P-H-I, I don't know why. I just call it phi. I could call it fancy phi, because it's a little fancier looking. I personally put a t in a superscript there, and put a y here. Some people put the t in a subscript, kind of like this y0 is in a subscript. I prefer putting it in a superscript because we're going to see that this thing ends up satisfying some properties that are similar to exponents. This t is not an exponent, but we'll see that it kind of acts like an exponent. And that's in the reading. How much time do we have here? 3 minutes. What is this thing? Well, first of all, its formula is the exact same formula. This thing, y e to the negative 2t, so why all the different notations? Is it to be purposely confusing? Well, no, it's actually ultimately for clarity, but it just feels confusing at the start. Ultimately, it's for clarity in emphasizing different things. This notation here emphasizes that this function is a function of t, and as a function of t, it's a solution, because solutions are functions of t. And the subscript just emphasizes that's the initial condition. This notation emphasizes that, well, if I want to in this one, I could think of y as a variable. And I could think of this as a two-variable function in two quantities t and y. What does this notation emphasize? This notation emphasizes that, in a sense, I could really think of the solution as generating infinitely many functions of y, which should prompt you to ask why. For each fixed t here, we get a function of y, and in fact, it's a simple function of y. If t is fixed, it's a constant times y. e to the 2t is going to be a constant. And the graph of this as a function of y is going to be a straight line with a slope of e to the negative 2t, and through the origin, since there's no constant term that's being added here, the slope of this thing as a function of y is going to be e to the negative 2t for fixed t. But then if I let t change, that slope will change. I'll get an animation that'll show me a bunch of different straight lines through the origin. I think before I put Mathematica up on Moodle, I'll make it a manipulate animation that does that for this example. But again, you should ask why. Why would we ever consider such a thing? Why put ourselves through this stuff if it's not in the textbook? Okay, again, the main punchline, the main benefit for us of thinking this way is going to come especially in chapters 3, 4, and 5, maybe even a little bit in chapter 2. We're going to be able to make some really cool animations in Mathematica based on this idea, and also do some cool mathematics stuff in class on the board by hand if we work at understanding this notation. And that's the main thing I'm trying to get across right now, is just understanding this notation. It turns out, and you'll see this in the reading, I'll just summarize it here right now, that when you iterate this function for fixed positive values of t, at least in nice cases, one case being nice is the fact that this is autonomous. Another nice fact about this thing is solution curves don't blow up in finite time. There's no vertical asymptote here for your solution function. If you iterate this function for fixed positive values of t, for nice examples like this, that will tell you information about what's happening to the y values of solution curves. But it only works nicely when the equation is autonomous. It actually doesn't work at all when the equation is not autonomous. And for autonomous equations, it only works really nicely when solution curves don't blow up. They don't have any vertical asymptotes. Okay? Do the reading, okay? We'll talk about it more on Friday. See you then.